Hello, my name is Clifford Collins and I'm here with Ayo. And today we are going to talk about fluorescence, the third lecture in the biophysics lectures. So we're going to start with fluorescence. I have my lecture slides on my phone. I can't show it because obviously it's copyrighted. So we're going to start with the introduction to fluorescence. So the first thing is the electromagnetic spectrum. So the electromagnetic spectrum is what is a group of waves, group of electromagnetic waves ranging from gamma rays to radio waves. So which one has the lowest energy? Gamma rays or radio waves?
Radio waves.
Radio waves, exactly. So we know that we have seven groups of rays, right? So gamma rays, then
Um, X-rays.
yes, X-rays, and then
UV.
yes, UV, ultraviolet, right? And then after UV, we have the visible. And invisible, we have different colors, right?
Right.
So yes, so the colors with the highest energy is which one?
Violet.
Violet, exactly. So that's why ultraviolet is just above violet, right? And the one with the lowest energy is
Red.
red, exactly. So then below red in the visible light is which?
Infrared.
Infrared, exactly. So infrared is below red. Then below infrared is
Um, Microwave.
yes, microwaves, and then
Radio.
radio waves. Perfect. Exactly. So this is in decreasing energy. Nice. Also, it's also in decreasing frequencies, right? Because we know that energy is directly proportional to your frequency, right? Your energy is equal to your HF, right? What is H?
Planck's constant.
Exactly, Planck's constant. And we know that our frequency is inversely proportional to our wavelength. And our frequency is equal to our C over lambda, right? This is
I've never seen this before. Okay, see, okay, speed of light.
speed of light,
Okay.
right? Nice. Okay.
Yeah.
Yeah. Okay. Yeah. Yeah, exactly. You can, to cross check, you can just check the unit. Frequency is per second, speed of light is meter per second, wavelength is meters. So they cancel out.
Okay.
I mean, you can just cross check it and
Yeah.
make sure that you're doing the right thing. Okay, so that means if your frequency is decreasing, as you're seeing here, decreasing frequency, so your frequency is decreasing, what happens to your wavelength? Increases. So this is increasing wavelength. Right? Increasing wavelength. Okay, so that is it for the electromagnetic spectrum. We have 7 different types of waves. There's nothing else, right? Nope. Frank Heck's experiment is next. What's Frank Heck's experiment? Frank Heck's experiment.
Um, in the experiment for the proof of quantum energy.
Yes. So it's an experiment to show that atoms take up energy in quantum. So they take up energy bit by bit, not continuous. So it's an experiment to show that energy uptake by atoms is quantized. Quantized. So that means atoms take up energy in photons, right? What's a photon?
It's like quantized packets of
Exactly. So photons
energy.
are packets of energy, right? Packets of electromagnetic radiation or energy. So packets of energy. So the energy uptake is not continuous, right? So it's not continuous, right? That's the Frank-Hertz experiment. So let us explain the Frank-Hertz experiment. We have we have our cathode, we have our grid. You know what grid is, right?
No.
Grid is like meshwork, network.
Okay.
Yeah. So we have our cathode. There is a positive potential difference between our cathode to our grid. That means you're approaching positive. So our grid is positively charged and our cathode is negatively charged. And there's a negative potential difference between our grid and our anode. So you're approaching negative. So our anode is negatively charged. You understand, right? Nice. Okay, so our cathode is heated.
Oh, is anode not positively
Now, in
charged?
this case, the
It's negative.
cathode and the anode, they are both negative.
Oh,
Yeah,
yeah.
the grid is positively charged. Nice. Okay, so our cathode is heated, right? So when it's heated, electrons are emitted. So we have thermal emission of electrons. Emission of electrons at the cathode, right? The cathode is heated and electrons are emitted. So now your electrons here, they're emitted, and there's a positive potential difference. Positive potential difference. You know, the potential difference is basically the ability to do work, right? So if there's positive potential difference between our cathode and our grid, that means the electrons, work can be done on the electrons, right? Nice. So work can be done on the electron. And as a result, the electron is going to gain energy, right? So work done on the electron is going to be equal to the energy gained by the electron. So if we assume that the electron is released from the cathode at zero kinetic energy, all of the work done on the electron by this positive potential difference is going to be equal to the kinetic energy of the electron. You understand? Nice. So the work done by the electron is equal to our charge times our potential difference. Okay, so charge of the electron. So what's the charge of electron? It's given as value E, right? Then times the potential difference. Let's say our potential difference is called V. So V is equal to big V is equal to half mv squared, right? So that means our EV is equal to half mv squared, right?
Yep.
This is big V. Okay, let's say that our potential difference here is 1 volt, right? So it's going to be E times 1 volt. So it's basically 1 EV, right? Basically, half mv squared. So our EV, electron volts, can be seen as a measure of energy. right? Electron volt can be seen as a measurement of energy, right? Okay. So it's given by the energy of the electron is the potential, is the kinetic energy, right? And it's given by the positive potential difference.
Okay.
So the higher the positive potential difference, the higher the kinetic energy.
So if the potential difference is zero, nothing
Zero.
will happen to the electron.
Exactly. The electrons will not move.
Move. Okay.
Exactly. Nice. Okay. So the electrons are going towards the grid. When they reach the grid here, they're going to be faced with a negative potential difference. Negative potential difference between the grid and the anode. Right? So if this positive potential difference is going to do work on the electron to give the electron energy, what is a negative potential difference going to do to the electron? It's going to take energy from the electron. You understand?
Okay, positive gives it energy,
Energy
to move.
towards the grid,
Okay.
and the negative takes
Takes
away
off its energy.
energy when the electron is moving to the anode.
Okay.
Nice. Okay, so the negative potential difference between the grid and the anode is used um, decelerates the electron, right? Decelerates the electrons, the electron. Okay. So now let's add mercury atoms to it here. So the electrons are coming out from the cathode. Why are they coming out from the cathode?
Because it's being heated.
Yes, it's being heated. Exactly. So they're coming from the cathode and they are being accelerated towards the grid. Inside here, between the cathode and the grid, you have atoms, mercury atoms. You can imagine it, you have them everywhere. I mean, at low pressure. It's not that important, but. So you have mercury vapor, mercury vapor. Okay, so the electrons here, when they are accelerated towards the grid, they are going to gain energy, right? And they can give some of that energy to the mercury atoms. So when they give some of the energy to the mercury atoms, they can excite some of the electrons in the mercury atoms. So let's show the example here. You have the nucleus. You know what excitation is, right?
Yes.
What's excitation?
When an electron moves from a lower energy state to a higher energy.
Exactly, exactly. Nice. So you have this electron coming here from the anode and from the cathode. They hit the electron here in the mercury atom, and they can excite it to go to a higher energy state, right? So the energy that is needed to go from this energy level to this energy level is fixed. E2 minus E1 is fixed, right? So, so the electron coming from the cathode must have exactly that energy so that before it can transfer energy, right? What if it doesn't have enough energy? If the energy here is less than E2 minus E1, what happens?
Um, it won't be excited.
Exactly, there will be no energy transfer. You understand, right?
Yes.
So the energy of the electron must be exactly equal to the energy that you need for you to have energy transfer. If it's greater, there will also be no energy transfer. But we don't see that scenario. We're going to explain why. There will be no energy transfer. Yeah, transfer. Okay, you understand, right? Okay. So the electron is coming from here. Let's say that the energy that is needed to excite it, this E2 minus E1, let's just give it a fixed value. Let's just say it's 35 electron volts. And let's say that we have the potential difference from your cathode to your grid. Let's say it is, we're going to be changing the value. Let's say it is 20 volts, the potential difference here is positive, right? So what is going to be the energy of the electron when it reaches the grid?
Zero.
No, it's 20
Volt.
volts. So the energy of the electron, we said energy of the electron
Oh, okay.
is going to be, yeah, E times V, right? So it's going to be E times 20V. So it's going to be 20 EV, right? Nice. Okay. So since it is less than the 35 electron volts that you need, what's going to happen?
It's less than.
Yes, the energy that the electron has is less than the 35 electron volts that is needed to excite the mercury atom.
There will be no energy transfer.
Yes, there will be no excitation, exactly. So the electron is going to pass through this the cathode and anode region, and it's going to pass through and it's going to start going towards the anode, right? Now let's say that between the grid and the anode, you have a negative potential difference, small negative potential difference, minus 0.5 volts. Remember, the negative potential difference decelerates, right? So the electron will lose 0.5 electron volts every time when it passes from the grid to the anode all the time. You understand?
Yes.
So since the electron did not have any energy transfer and will have 20 electron volts at the grid, that means it can pass through and reach the anode.
Yeah.
You understand? So there's going to be current. You understand, right? Nice. Okay, now let's give another scenario. Let's say that the potential difference between the cathode and the grid is 40 plus 40 volts. And the energy you need to excite is 35 electron volts. What's going to happen?
There'll be excitation.
Yes, why would there be excitation?
Because the energy of the electron
Yes.
is more than the this
Yes,
yeah the excitation.
exactly. So we can think about it in this way. If we have 40 electron volts, 40 volts, we can divide this potential difference into two regions. We can divide it into the first 35-volt region, and we can divide it into the next 5-volt region. So at this point here, at the edge of this 35-volt region, the electron here is going to have exactly 35 electron volts, right? And at this point here, the electron is going to have exactly the energy needed to excite the mercury atom. So at this point here, the electron is going to give all of its energy to the mercury atom. And its kinetic energy is going to reduce to zero.
Okay.
So at this point, its kinetic energy will be zero. And then it will move the extra 5 volts region. So it's going to be accelerated for this region again. You understand? So the energy that it's going to have here is going to be extra 5 electron volts when it gets to the grid. You understand, right?
Yeah.
Nice. So since it gets to the grid with 5 electron volts, it's going to afford to lose the 0.5 electron volt and it will reach the current. It will reach the anode and there'll be current. You understand, right?
Yeah.
Nice. Okay, so that means at 40 volts there'll be current at the anode, At 20 volts, there will also be current. But the difference is that 40 electron volts, there'll be excitation. 20 electron volts, there'll be no excitation. Right? You understand, right?
Okay.
Nice.
But what's the use of the electron getting to the anode when there's an excitation?
Nothing. It's just, yeah. The important stuff is what happens at 35 volts.
Okay.
That is the secret. Okay. So what happens at 35 volts? So you have your cathode, right? You have your grid, you have your anode grid. What is the charge in your, what's the sign for your cathode?
Negative,
Negative. What about your grid?
positive,
Positive and
negative.
negative. Exactly. So you have a positive potential difference, right, between your cathode and your grid. Don't forget, positive potential difference means that you can accelerate the electron, right? And you have a negative between your grid and your anode. Negative potential difference, right? So that means you decelerate. That means you lose kinetic energy, right? This gains kinetic energy. Okay, so let's have the potential difference between your cathode and your grid, exactly 35 volts. And the mercury atom needs 35 electron volts. So the electron is coming from the cathode, right? And it's going towards the grid. So when the electron gets to the grid, yeah, because the potential difference is 35, it's going to have exactly 35 electron volts at the grid. Exactly that, right? And there's going to be a mercury atom waiting because it just knows. And at the grid, the electron is going to give all of its energy, all of the 35, because the mercury atom needs 35 electron volts. So the electron is going to give all of its 35 electron volts to the mercury atom. So what will be the energy of the electron? Now,
No energy.
exactly, it will have 0 electron volts, right, at the grid now. So now this electron has 0 electron volts. It cannot overcome this negative potential difference. Because to overcome this negative potential difference, you have to lose,
The atom.
yes, you have to lose 0.5 electron volt, right? So because that's 0 electron volt energy, it cannot overcome the negative potential difference. So is there going to be current or no current?
No.
No current, exactly, because if it cannot overcome the negative potential difference, it cannot reach the anode, and there will be no current. You understand, right? Nice. Okay, so what happens if the potential difference is not 35? Let's say it's a multiple of 35. Let's make it a bit harder. Let's say it's 105 volts. So what happens?
This will take the mercury take up the energy
Where? When?
at this place.
At the grid?
Yes.
No, no, no. Don't forget, 105 electron, 105 volts is the same thing as 335. The same thing as 335. That means at this point here, the electron will have exactly 35 electron volt energy. And at this point, it's going to meet the mercury atom and it's going to give it all of its energy. So its energy is going to reduce now to 0 electron volt. Then it's going to continue again. At this point here,
Give another
yes,
mercury.
exactly. Give another to reduce to 0. Nice. Then
But what
it's
if
again
like the number is not equal, like 105?
Yeah. If the number is not equal, like, what do you mean?
Like, you can split this into
Yes.
35, 35,
Yes.
35. What
Mm-hmm.
is like 106?
Exactly. Okay. It's okay. So if it's 105, at this point here, it will have zero electron volt, right?
Yeah,
So it will have no energy to reach the anode.
yeah.
So there'll be zero current. If it's 106 electron volt, you can split it into 35,
35,
35,
36.
35, and
Okay,
then
okay,
1 volt. So it's going to have 1 electron volt when it gets to the grid, at the grid, right? So that means it's able to reach the anode.
okay, so the
So
current.
that we current. You understand, right?
Yep.
So you're going to have a graph that's like this, where at every point 35, at every multiple of 35, 70, 105, 140, at every multiple of 35, the current, this is a graph of current, and what's on the x-axis?
Um, Potential difference.
Mm-hmm. What potential difference?
The between cathode and the grid.
Exactly, potential difference between the cathode and grid. So at every multiple of 35, this current is going to drop almost to zero. You understand, right?
Yes.
To drop almost to zero. That's how it goes. You understand, right? Nice. So this is the Frank Hertz experiment. It shows that the energy uptake by atoms is quantized. So you can only accept a fixed amount. You cannot accept more, you cannot accept less.
Okay.
Nice. Okay, so next. Oh yeah, we're going to take a break now.
Okay.
Yeah, 5 minutes break.
Can I take a picture of like?
I'm going to send you the pictures.
Oh, okay.
Yeah, don't worry. Send you the pictures. I'll put it on my website. I have a website. Oh my god.
How often will you be posting?
I don't know. It depends on how I'm lazy.
And you have to like edit.
No, I'm not going to edit. I'm not going to edit this. So whatever you say now is good.
Wait, what I'm saying now?
Editing takes a lot of time.
Yes.
God, I tried editing once. I'm never doing it again in my life. Okay, 5 minutes break. But you understood, right?
Yes.
Okay, let's start. It's now to. Okay, so next is the spectrum of hydrogen, the line spectrum of hydrogen. Okay, so the line spectrum of hydrogen right now, this is talking about the electronic transition. What is electronic transition, Aya?
Electronic transition. I don't know.
It's just movement of electrons
Okay.
from one energy level to another. We have other types of energy levels, so we have to specify it. So from one electronic energy level to another, we actually have three types of transitions, so three types of energy levels. So three types of energy levels. Can you tell me the three types of energy levels? The first one is electronic energy levels. That is the number one we know in chemistry. Mhm. We have the rotational energy levels. And we have the vibrational energy levels. So you can imagine an atom having energy levels like this. So this is n equal to 1, right? Your normal electronic energy levels. Then in between your electronic energy levels, you're going to have um, rotational energy levels, or whichever one is next. And then in between, you're going to have even smaller. I'm going to show you the dotted lines.
This is electronic.
The big ones here, the one labeled n equal to 1, n equal to 2, n equal to 3,
Okay.
the electronic energy levels. You're going to have smaller ones, like rotational energy levels. That's this one here, rotational energy levels. Then in between the rotational energy levels, you're going to have even smaller ones, like the vibrational energy levels. You understand?
Yes.
Nice. Okay. So when you're explaining the line spectra of hydrogen, if it happens in a vacuum at 0 Kelvin or something, so when there's no temperature effect, then you're only going to see electronic transitions. You understand that? So line spectrum of hydrogen will mostly is talking about electronic transitions in a vacuum, low temperature. Because when we're going to talk about it later, when it's not in a vacuum or when the temperature is high, you're going to see some other effects that's going to cause widening the line spectra. So not the fine line spectra. Okay, so line spectra is just the movement of let's show the electrons instead. It's just going to be given by the movement of the electrons, right? Right?
Yes.
From one energy level to another. Right? So when it's going from this n equal to 1 to n equal to 2, is it excitation or relaxation?
Excitation.
Exactly, excitation. So it's absorbing energy, right? So this can be seen in the absorption spectrum. What about the opposite? If it's going from n equal to 2 to n equal to 1,
Relaxation.
yes, this is relaxation. So this can be seen in the
Emission
yes,
spectrum.
emission spectrum. So in the absorption spectrum, you're absorbing energy. So you pass white light. This is white light. Through the atom, and it absorbs one. So one wavelength is missing. You can see this is the missing wavelength, right?
Okay.
Nice. So you're going to have, um, if this you have the light spectrum, you're going to have bright spot, and then one dark
Dark
spot.
spots.
Nice. So dark spot. Well, you don't usually have just one dark spot because you have more than one kind of transition. You have several dark spots, right?
Mm-hmm.
And the position of the dark spots will tell you the identity of the atom. Exactly. So the light spectrum is characteristic for each atom, right?
Yes.
So characteristic is very important to remember that it's characteristic. And the emission spectrum is the opposite, right? So you can excite the atom first. Let's say you heat the atom. So apply heat because it's useful to excite the atom with something other than light because you're trying to measure light. So it's better to excite it with heat or something else so that when there's going to be relaxation, it gives out a particular wavelength, right? And then you're going to have, we have the spectrum. You're going to have one bright spot, right?
Yes.
Bright spots. So the position of this bright spot and the position of this dark spot is exactly the same, right? Nice. So you already know that.
Yes.
Okay, so we already talked about that. We have different types of lines in it. The Lyman series, the Bauman series, and the Paschen series. It's just something to memorize. The Lyman series is always to or from the first energy level. So Lyman series is a series of transition. So it's a couple of transition, series of transition, of electronic transitions to or from the first energy level, n equal to 1, right? And then Bauman series is to or from n equal to 2, right? Now, Paschen series is to or from. Okay, so basic stuff. Next is talking about the other type of transitions that is not electronic energy, that is not electronic transition. So we mentioned that there are other energy levels, right?
Yes.
The vibration and the rotation energy levels. So this is a bit useful. That means if you have an electron that is excited, there are several ways for the electron to relax. That is besides electronic transition. So it can relax step by step. So you understand, right?
Yeah.
Yeah. So you can. So that is the use of this electronic, the use of these non-order energy levels. There are different ways for the electron, the excited atom, to um, release energy. So different routes for the excited atom to release energy. Okay, now let's talk about the, so we already mentioned that narrow spectral lines can usually be seen only when you have in a vacuum, right?
Yes.
Vacuum and low temperature. Because in a vacuum, you have no interacting molecules. So no interacting molecules. So that's when you're going to see your narrow spectral lines. But when you have interactions with other molecules, for example, the interaction of the particular hydrogen atom with a solvent or with some other molecules is going to cause a widening of your spectral lines. So instead of seeing a single line, you're going to have bits. You understand, right?
Mm.
So this is widening. So this widening, when it's due to interaction with solvents, solvents or other neighboring molecules is called heterogeneous effect. You understand, right?
Yes.
So it's called heterogeneous effect when the spectral lines widen due to interaction with solvent or other neighboring molecules, right?
Yes.
Nice. So that's just it here. So because of the um, interactions, that's why instead of having for some complex molecules in a solvent, instead of having just narrow lines for the absorption spectra, we have a basic curve, like this complex curve. You understand? This is your wavelength. This is your intensity. So this is due to the heterogeneous effect. You understand?
Yes.
So absorption spectra.
This interaction with solvent molecules.
Yes, solvent and neighboring molecules
Okay.
can cause instead of having lines in your absorptions in your as your absorption spectra, you need to have curves
Okay.
like this and stuff. You understand, right?
Yes.
Nice. Okay, so that is it here. So the next is we're going to talk about the instruments for measuring absorption and emission. Okay, so we're going to talk about our photometer and our fluorometer. Okay, before we talk about our photometer and our fluorometer, it's important to just go back to the beginning and talk about interactions of matter with light. Sorry, but it's important. Um, Light is basically photons. It's not just visible light, it's photons we're talking about here. Okay, so if you have a body, an object, and light strikes the object, this is incident light, right? Incident light is light that strikes the object. There are three things that can happen to the light. What are the three things that can happen to the light?
Reflect,
Reflection, perfect. Mhm.
refraction,
And transmission is
transmission.
correct.
Okay.
Transmission. Mhm.
Um,
And absorption.
absorption.
So these are the three interactions, right, of light with matter. Okay, so we learned in thermal radiation that when an object absorbs radiation, it also emits radiation later, right?
Yes.
Nice. So in order to maintain thermal equilibrium, so in order for the temperature not to increase, the energy that the object absorbs is usually equal to the energy that the object emits, right? Nice. So that is basically it here. So when an object usually absorbs light, it emits the radiation in terms of heat most times. But sometimes some objects will absorb light and will emit the radiation in terms of light. So what is this called?
Emitting.
Yeah, as light. So they emit the radiation as light. What is it called when an object emits radiation as light?
Emission.
Yes. There's something else. It's called luminescence.
Oh, okay.
Luminescence. I'm not sure this is the right spelling. So luminescence is the emission of light by a body after it has been excited. There are two types of luminescence. What are the two types of luminescence?
Fluorescence.
Yes, perfect. So you have the immediate luminescence, right, which is fluorescence. This is the one that happens in about 10 to minus 15 seconds, right?
Yes.
Then you have the delayed luminescence, which is what?
Phosphorescence.
Yes, thank you. Which is phosphorescence. And this can take up to several minutes, right?
Yes.
Exactly. Okay, so in order to detect, now let's go back to detection of photometer and blah 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 blah. Photometer. What does the photometer detect?
Um, Light.
Yeah, what kind of light?
Visible light.
Yes, but does it detect reflected light, absorbed light, or transmitted light?
Transmitted.
Yes, it detects transmitted light. Detect transmitted light. And the aim is to find out the amount of the intensity of light that is absorbed. So it detects transmitted light in order to calculate the absorbed light, right? Absorbed light intensity. Okay, because you want to detect the transmitted light, you have to put the detector in the same path of light as the source. You understand, right?
Yes.
Nice. So this is your source of light. You have your monochromator. What's the function of your monochromator?
To get one wavelength of light.
Yes, to get a certain wavelength of light. Because most times you want to study just a certain range of wavelength. So it selects a wavelength, select a wavelength or a small um, range of wavelength. And then this is your sample. Right? This is your sample. And this is your detector. You understand that?
Yes.
The sample absorbs some light and also transmits some light. Right? So imagine if you imagine that reflection is minimal, then the light intensity absorbed is going to inversely be proportional to the light intensity transmitted, right?
Mm-hmm.
Right. So our absorption is going to be inversely proportional to our transmission. Then transmission. You understand, right?
Yes.
Assuming reflection is negligible. Reflection is negligible. Negligible. Okay, so it's important in a photometer. A photometer measures the transmitted light in order to measure the absorbed light. And the detector is in the path of the light source. You understand, right?
Yes.
Nice. Okay, let's go to the next one. What's the next one? Next one is your fluorimeter. What does your fluorimeter detect?
Flows.
Yeah, it does. It
Um,
does.
the
Yeah.
do we need to know like the equation
Yes.
on that photometer?
Yes. We are going to talk about it. Mhm. It is fluorescence. Okay. What is fluorescence?
Decay from excited singlet state of a fluorescent.
You're cheating. Okay. Okay. Fluorescence is just emitted light. Basically. Okay. So you're looking for the emitted light. So you don't want the transmitted light. So that is why if you have your source here, no, not your source. Yeah, okay, let's just say your source here. You have your source, and the light is going in this direction, passes through your sample, and it's going in this direction. This is your transmitted light, right?
Yes.
You don't want this transmitted light, sorry. You don't want this transmitted light. This is you have your monochromator. So what do? You want your emitted light, right? You want the light that's going in every direction. Emitted light is going in every direction, but you don't want this transmitted light. So you have to put your detector 90 degrees away from your transmitted light. It's not because this is the best place to detect the fluorescence, it's just because this is the best place to avoid the transmitted light. Because transmitted light is going to be very high intensity compared to the emitted light. Yeah. So you put your detector 90 degrees away from that. Okay. So now let's go back to the equation that you mentioned. The transmitted light intensity compared to the incident light intensity. Okay, that's Lambert-Beer law, right?
Yeah.
So what does it say?
Mm, I don't know.
You have your incident light and you have your transmitted light. Your transmitted light is given as I, your incident light is given as IO. Incident light intensity. I is your transmitted light intensity. IO is your incident light intensity. Incident light intensity. Okay, so what is your I? Your I reduces, right? It reduces, it decays, right? Like you mentioned. So your I, your transmitted light intensity is equal to your IO times 10 raised to the power. This is different form. Normally you have E raised to the power, but here you can have 10 raised to the power.
Okay.
Epsilon C L. Okay, so this L here is what? What's the L? L is the,
Distance.
yes, the distance the light travels in your sample, through your sample. That's the L. L is equal to the distance light travels through the sample. What is C?
Molar concentration.
Exactly, molar concentration. And your E is just a constant. Just a constant. Your absorption coefficient. You understand, right?
Yeah.
Yes. So you can see that if your length increases or your concentration increases, then the transmitted light intensity is going to decrease. Yeah.
Light in length increases.
Yes, if the length increases or your concentration of your solid increases, the transmitted light intensity is going to decrease. Why?
Um, because when like the sample is concentrated,
Yeah.
it's more colored.
There will be more molecules to absorb.
Yes.
Exactly. That's just it. There will be more molecules to absorb. You understand? If your length increases, there'll be more distance for light to pass, and there'll be more samples, more molecules to absorb. You understand, right?
Yes.
Okay. So don't forget, you can also write it as your I is equal to IO times your E raised to power minus, under X. Usually, it can be something like this, because you know what you're writing. You understand?
Yeah.
Yes. Okay. So, what is the definition of fluorescence? Let's go to the next slide. Oh, no, no, no. Let's talk about the A. A is the definition of absorbance. Absorbance is given here. Absorbance A. What's the absorbance?
Absorption.
Yeah, it's a measure of how much the sample absorbs the light.
Okay.
Yeah. So your A is given as log of what? Your, let's say IO over I. So here you can see that if your transmitted intensity I is high, that means less of the light was actually absorbed, right? And the absorbance is going to reduce. You understand, right?
Yeah.
Nice. So if you check later, you're going to see that transmittance, see, transmittance. What's transmittance? It's just basically the opposite. Log of I over IO. That means if your transmitted intensity increases, your transmittance is going to increase, right?
Yeah.
So they are both, yeah, opposites. You understand, right?
Yes.
Okay. So relating these two equations together, your A is given as your absorption coefficient at a particular wavelength. That's why it's irritating like this. Times your concentration times your length. You understand? This is absorption coefficient at a particular wavelength times your concentration times your length. So that means using the ratio, using the absorbance, you can be able to calculate the concentration of solutions. You understand?
Yes.
Especially dilute solutions. Because for dilute solutions, the the graph gives you a straight line. So you can easily calculate it. You understand?
Yeah.
Yeah. Nice, 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 nice. Okay, fluorescence. What is fluorescence?
Um, the emission
Uh-huh.
from excitement of a fluorophore.
Yes, yes. To what? To the
Normal
mhm,
or to a lower
energy
energy
level.
level
Uh-huh. Emission of light.
of light
Exactly.
from higher to lower energy level.
Exactly. Because it can, from higher to lower, can emit other things, not just light. It can emit heat.
Okay.
So relaxation is just the coming down from higher, like it's when it started. Nice. Okay, yeah, you're right. So is the um, emission of light when there's a relaxation. So emission of light after relaxation, during relaxation, emission of light during relaxation. But here in the lecture slides, is included from a from an excited singlet state. Mhm. So what does that mean? Let's show it. What is a singlet state?
A, an energy level
Yeah.
of a single state.
Okay, let's draw the our favorite diagram, our Jablonski diagram. Favorite diagram. You have this is your S0. This is your ground singlet state. Okay, to know the number of lines that this is going to have, to know if it's a singlet or duplet or whatever, to know number of lines that's going to be present is equal to 2 times the spin plus 1. So at this stage here, this is going to be like this. Okay. 2 times the spin plus 1. For here, what's the spin? The total spin for this.
The total spin
Mhm.
2.
No, no. It's half plus
Half.
minus half. Plus half plus minus half. So it's zero.
Yeah.
You understand, right?
Mm-hmm.
So the s is equal to zero. So the number of lines here, 2 times 0 plus 1. So it's 1. So this is singlet state. You understand, right?
Yeah.
This is also a singlet state, S1. It's also a singlet state, but this is an excited singlet state. This is a triplet state. Triplet state means it's going to have 3 lines in the line spectra, whatever. This is because it does something that is impossible. It is like this. So yeah, what is the total spin here?
Plus half plus half.
Yeah. So it's 1, right? S is
One.
equal to 1. So our number of lines is what? Is equal to 2 times 1 plus 1, right?
Yeah.
So this is 3.
Three.
That's why it's called a triplet state. You understand?
Yes.
There's going to be a duplet state, but we don't really care. Duplet state is if it's just unpaired, right? It's going to be a duplet state. Nobody cares about duplet. I don't know why. It's funny. Okay, so this S0 and S1, these are the electronic energy levels, right?
Yeah.
So remember, we don't have just electronic energy levels. We have other types of energy levels, right? Nice. Okay, let's take a break. We're going to continue. Yeah, for a break. I think I can use it. Okay, so we have the ground state, that's the S0, and we have the excited state, S1. So to go from ground state to excited state, what is it called?
Absorption.
Yes, absorption. Absorption or
Excitation.
yes, excitation. Then to come down from excited state to ground state is called what?
Emission.
Yeah,
Or
relaxation.
relaxation.
Relaxation. Actually, this is called excitation and
Relaxation.
relaxation. Absorption is because you absorb the energy, and emission because you are the energy. You understand, right?
Yep.
Okay. So remember, we said that we don't just have electronic energy levels. We also have other energy levels, right? What other energy levels do we have?
We have vibrational
Yes,
and rotational.
exactly. We have vibrational and rotational. So we are going to show it here. Vibrational, rotational, right? Right? Nice. Also the same thing here. And then, nice. And then also for the ground state here. Same thing happens. Okay, so so fluorescence is always following absorption. So fluorescence, it always follows absorption. Always follows absorption. And we said it's from the excited state, right? Okay. So now let's just go into details for the whole fluorescence, phosphorescence, internal conversion, Stokes shifts, blah blah blah, all of them. Okay, let's do it. Do you have any particular question about this?
No.
Okay, thank God. Okay. Okay, so you have absorption. Let's have the absorption go from here to here. This absorption or excitation. There are different ways to relax. There are two ways to relax. What are the two ways to relax? Two types of relaxation.
Two types of relaxation.
Mm-hmm.
I don't get it.
Yeah. So you can emit radiation or you can not emit radiation.
Okay.
So it's the what with radiative relaxation and non-radiative relaxation. Start reading you. Radiative relaxation and non-radiative relaxation. You understand, right?
Yeah.
So what are the two types of radiative relaxation? That's the luminescence, right?
Mm-hmm.
The two types of luminescence.
Immediate. Oh,
Yeah,
yeah,
immediate,
immediate and
which is
delayed. Immediate is
fluorescence,
fluorescence, while
and
delayed
delayed
is phosphorescence.
phosphorescence, exactly. So we can have non-radiative relaxation. Okay, so from here, from this point here, we are going to have some kind of relaxation. So it can be small here. So when you are at this point here, you have to relax to this level, maximum here. You cannot relax from here straight to here. Why? Because this violates Kasha's rule. Kasha's rule. Kasha's rule says that When you're relaxing, you have to relax to the lowest energy level of that singlet state before you can relax any further. You understand, right?
Yeah.
So you cannot relax straight from here all the way to here. No, that is wrong. You understand?
Yes.
Okay, so when you're relaxing here, this relaxation is very small, so it's not going to release a photon. So what do you call it? Since it relaxes and doesn't release a photon.
Non-radiative
Yes, it's a type of
relaxation.
non-radiative relaxation. But it's a special type of non-radiative relaxation called internal combustion. Yeah, internal combustion. Internal combustion is a type of non-radiative relaxation. Non-radiative relaxation between, you know, between the singlet states, basically. So this here is released as heat, basically, right? So this loss of energy is released as heat. So you can have also more internal conversion. This to here, stepwise, stepwise. So you can have series of internal conversion that just releases heat. When you're here, you can go from your S1, lowest energy state of your S1. Don't forget, you cannot go from here. You cannot go from here.
Okay, so these are like the rotational.
Yes, energy levels and vibration energy. Yeah, these are rotational energy levels. Yes, so you can go from this lowest S1 to your T1 state. What is this called when you go from your S1 to your T1 state?
Radiative.
No, not necessarily. This is called intersystem crossing.
Okay.
It's also reversible, but don't pay much attention to this back stuff. The most important one is from S1 to your T1. So you can go directly from your S1 to your T1. And then from your T1, you can come down to your S0. This is usually radiative, and this is called phosphorescence or delayed luminescence. And this is a forbidden transition. Why is it called a forbidden transition? Because you're changing the spin. You're going from your triplet to your singlet. You're changing your spin. So this has a very low probability.
So this is triplet as well.
Which one?
Um, the S1.
No. S1 is singlet. It's called excited singlet.
But shouldn't be it be forbidden as well?
No. Which one do you mean?
Because going from singlet to triplet.
Oh, you mean this intersystem crossing?
Yeah.
No, not necessarily. Yeah, it should be forbidden, but we don't really pay so much
Transition.
attention to it.
Okay.
We mostly talk about the phosphorescence as a forbidden transition because it has no probability of happening.
Okay.
So if you have a molecule and if you have a molecule that goes from S1 to T1, this molecule is going to spend a lot of time here because the probability of going down to S0 is low, right? So since it spends a lot of time here in your T1, that means that it's going to go slowly from your T1 to your S0, right?
Yeah.
So that's why phosphorescence takes a long time, right? A long time. So you can take from like 10 raised to the power minus 9 seconds up to 10 raised to the power 1 seconds, right? Or even longer. You understand, right?
Yes.
This is like a very long time in physics. You understand, right?
Yes.
Nice. Okay. So fluorescence, on the other hand, is like from this S1, maybe something like here. So this is radiate. So this is fluorescence. This is immediate. You understand? So this happens maybe in 10 to the minus 9 seconds. It's fast, right? It's very fast. And then from here, it can go down here, more internal conversion. You understand, right?
Yeah.
Okay. Yeah. Yes, let's talk about the Stokes shift. So you can imagine the energy the molecule absorbs during absorption is a lot, right? A lot of energy. So let's mention this energy E1. Then the molecule, the energy the molecule releases is small, E2, right? So E1 is much greater than E2 because some of the energy that the molecule absorbs is lost by internal conversion, a lot of internal conversion. You understand, right? So I'm going to write it. Some of the energy absorbed is lost by internal conversion as heat, right?
Yeah.
So the energy that is released in the photon is going to be much smaller than the energy that was absorbed, right? As E1. Nice. So that means the wavelength of the photon that is released, HF2, compared to HF1. The wavelength is going to be longer, right? That is released compared to the wavelength that is absorbed, right? You understand? Since it's going towards the longer wavelength, we say it's going towards the red wavelength. So this is called red shift.
Okay.
Nice. So this is the red shift or the Stokes shift. What is the Stokes shift or the red shift? Is when the emission spectrum shifts towards red light compared to the absorption spectrum. Nice. Compared to the absorption spectrum. Absorption spectrum. Yeah. Okay. You understand? So we have talked about internal conversion, we talked about Kasha's rule. Remember what Kasha's rule is?
Yes.
What's Kasha's rule?
Um, that's emission from.
Kasha's rule says that you cannot go from here directly
Right.
to here. You have to go from the lowest energy level of that singlet level. You understand that? Nice. So you cannot, yeah. So you have to go from the lowest energy level. That's Kasha's rule. Okay. Why is the phosphorescence, why is it delayed?
Because of forbidden transition.
Yes, because the forbidden transition. Why is it a forbidden transition?
Mm, the what's it called?
Spin.
Spin changes.
Exactly, the spin changes. Okay, so the next thing we're going to talk about is the lifetime of the processes. What is lifetime?
Mm, like
70 years.
yes, the time it takes to die.
Yeah, but in practice, what does it mean?
The amount of time it takes the of emission.
No, not necessarily. Lifetime is almost like half-life. Half-life is the time it takes for the number to reduce to 50%.
Okay.
Right? Lifetime is the time it takes for the number to reduce to 63% to 37%.
Okay.
So the time it takes to reduce by 63%.
Okay. So it has like a constant.
Yes, it's just basically. You understand, right?
Mm-hmm.
Lifetime is the time it takes for the number of excited particles to reduce by 63%. Yeah. Okay. So let's look at the lifetime of the various processes. The lifetime of absorbance, that means the time it takes for 63% of the molecules to go from ground state to excited state, is very fast. Absorption is very fast. It's the fastest. It's around 30 to the power minus 15 seconds.
But fluorescence is 10 to power minus 9.
Yeah, it's fluorescence. Yes, fluorescence is mhm,
Okay.
30 to the minus 9, about 30 to the minus 9. And then phosphorescence is really, really short. Oh, is it no, not 30 minus 9, it's really small. Like 30 minus 6 seconds to really high number. You understand? It's a long time, not as small as 30 minus 9
Okay.
for phosphorescence. You understand, right?
Mm-hmm.
Nice. I mean, it's in lectures that you can just memorize this shit. So I shouldn't say shit. Okay, so that's it. You understand, right?
Yeah.
Okay. Okay, the next slide is talking about just the difference between the singlet and the triplet states, stuff like that. We already talked about the singlet state, right? You said singlet state has zero net spin, so it has one line because we have equation that we showed you. Remember, right?
Yeah.
Yeah, number of lines, blah blah blah. Number of lines is equal to the spin 2s, 2 times the spin plus 1. We say triplet state has 3 lines. Okay, so the next slide is talking about, is showing you that fluorescence has a higher energy than phosphorescence. Can you explain why?
Um,
Fluorescence has a higher energy than phosphorescence, usually.
because it doesn't have to pass through as much like states
Uh-huh.
as phosphorescence.
Yeah, so because the S1 is higher than the T1, right?
Yeah.
So this is fluorescence, this is phosphorescence. S1 has a higher energy level than the T1.
Okay.
That's just it, right? That's it. There's nothing else. Okay, okay. Okay, let's talk about the critical fluorescence parameters. Critical fluorescence parameters. Okay, so these are the parameters that can be used to describe fluorescence. Okay, what are they? They are, let's mention them. Can you mention them?
I should read it out.
Spectral distribution, just mention.
Okay, spectral distribution, um,
Photon yield,
brightness,
lifetime of excited state, and the polarization of the fluorescent emission. Okay, so the easiest we're going to talk about is the spectral distribution. Yeah, spectral distribution is very long. So let's take a break. I will talk about it after this 5 minutes break. Do you have any question?
No, I'm still looking. Oh, sorry, this.
Spectral distribution. We have two types of spectral distribution, right? What are the two types?
Um, Emission spectra and excitation spectra.
Exactly. Yeah. So spectral distribution is just the intensities, right? of light at each wavelength. Yeah. So we have the emission spectra, and we have the excitation spectra. So what is the emission spectra? What is the excitation spectra?
Emission spectrum. Um, can do emission wavelength. I don't understand what
But what is it basically? Yeah.
the excitation
Yeah.
of
Relaxation.
yeah relaxation.
Yeah. Yeah, relaxation. So first, what do? You before you have emission, you need to have
Absorption.
yes, exactly.
Excitation.
So it follows absorption. So it's very important. It follows absorption, right? So you have to absorb, you have to excite the molecule, and then you have to um, measure the emitter intensity at each wavelength, right?
Okay.
So excite the molecule, and then measure the emitted intensity. That's what I mean here. Emitted intensity at each wavelength. Okay, so that's it. What about excitation spectra?
That's um like absorption.
Mm-hmm. So how do you do it?
It follows absorption.
No, this is absorption.
This
The excitation
excitation. Okay.
spectra.
This is the first one.
Hmm.
So
So you just measure the absorbed intensity at each wavelength. You
okay.
understand?
Emission is you measure
You first excite it,
mhm,
and then you measure the emitted intensity
emitted.
at each wavelength. But in this one here, while exciting it, you measure the absorbed intensity at each wavelength. You understand, right?
Yes.
While excited, measure the absorbed intensity at each wavelength. Okay, let's guess. Which one do you use a photometer for? Which one do you use a fluorometer for? What is a
Um,
photometer? What is a fluorometer?
photometer is used to measure transmitted light.
Exactly. So we measure the transmitted light, and we use the transmitted light to measure the
The
absorption.
absorption.
Exactly. So which one can we use to measure the excitation spectra? Photometer or fluorometer?
Photometer.
Exactly. So you use a photometer. You understand, right?
Yes.
You use a photometer because a photometer can measure the absorption using the transmission, right? Using the transmitted light intensity measures absorption, measures the absorption of light by measuring intensity, by measuring the transmitted intensity. And the emission spectra uses which one?
Fluorometer.
Exactly. So it uses a fluorometer. Okay, so the next slide just shows how the two relate to each other. So if this is the wavelength, and this is the intensity of light, how does it relate? Which one is B, which one is A?
Which one is B?
Yes, is B emission or excitation spectra?
Emission.
Yes, why?
I don't know.
Because emission spectra has lower energy, right? Remember Stokes shift. Stokes
Mm.
shift means that you're going to emit less energy than you absorb. So less energy means higher wavelength, right?
Yeah.
So the wavelength is towards the higher wavelength compared to the absorption, right? You understand?
Yes.
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 So lower energy, higher wavelength because of Stokes shift. Okay, so let's talk more about absorption. I mean, we have already talked about the photometer
Yeah.
and the fluorometer, so there's no point repeating it again. We've already talked about the transmittance, we've already talked about the absorbance. I mean, let's just skip it. We already talked about it, right? There's no point repeating again. Let's go to the critical fluorescence parameters, the other fluorescence parameters. So we have talked about the one fluorescent parameter, which is the spectral distribution. The next is going to be the photon yield. So what is photon yield?
The amount of photons.
Mhm.
Yeah, gotten.
Amount of photon.
Amount of photons.
Mhm.
Like,
Emitted.
yes.
Mhm. Over amount of photons.
Absorb. I don't know.
Yeah, absorbed.
Okay.
Exactly, absorbed. Exactly. Why? Why is it that the photon yield is not always equal to 100?
Because some have been absorbed.
Huh? Some absorbed is not emitted as light. Emitted as light.
Okay. Okay.
Why? Why is because some that is absorbed is not emitted as light. How is the energy released?
Smaller.
Yes, but as heat.
Okay.
You understand? So some yeah. So some photons absorbed is released as heat, not as light, not as photons, right? You understand, right?
Yes.
Some photon energy absorbed. Some photon energies absorbed. It's released as heat, not as light. So that is what do we call it?
What?
When the photon energy is absorbed, it's not released as light. It's released as heat.
Non-radiative.
Exactly. Non-radiative relaxation. Right?
Yes.
Nice. Okay. So What are the different types of non-radiative relaxations we have?
Internal conversion.
Yes, internal conversion,
Um,
intersystem crossing
okay.
is also a non-radiative relaxation. Yeah. So, and then fluorophore is the radiative, right? So, you can say the photon yield is equal to the constant, the rate constant, whatever, basically how fast the fluorescence is happening. Rate constant for fluorescence, which is um, Kf over rate constant for fluorescence plus rate constant for internal conversion plus rate constant for intersystem crossing. Do you understand? Nice. So that is it. That is the photon yield. Okay, the next thing is brightness. What is the brightness?
Um, intensity of light.
Mm-hmm. Yeah, just intensity of light that's released. Exactly. Intensity of fluorescence. Okay, total fluorescence is the next one, which is stupid. Let's just give it. Okay, fluorescent lifetime. So what do you say fluorescent lifetime is?
Fluorescence lifetime.
Mm-hmm.
The half-life.
No, no. Half-life is different from lifetime.
Sorry, this photon yield. You
Yes.
said rate constant of fluorescence
Mm-hmm.
Kf
Yes.
is over.
All of the other rate constants, all the total rate constants.
Okay.
So that's where you have rate constant for fluorescence, rate constant for internal conversion, rate constant for intersystem crossing. You'd have had rate constant for phosphorescence, but it's very low. So you can,
Negligible.
it's yes, it's forbidden, right? Don't forget.
Okay.
So it's very, very low. So you can add it if you want, but it's not going to change much.
Okay.
Okay, what is fluorescence lifetime?
Fluorescence lifetime.
Mm-hmm. Or you can say the lifetime of the excited state. Mhm. So it is the time taken for the number of excited fluorophore to reduce by 63% of its original value, right? Or to reduce to 37% of its original value. What is the no, half time?
Half-time.
Half-life.
The time it takes from the 63% to
Yeah. Yeah,
really
yeah, you can say 63% to what?
37.
No,
So half of 63.
no, no. A half-life, just say from the beginning.
Oh, like normal half-life.
Yeah, normal half-life.
Um, the time taken for like
The number of excited starting
yeah
at
to reduce
say from
by
beginning.
half.
Sorry.
The time taken
Mm-hmm.
for the number of excited photons
Fluorophore.
fluorophores
Mm-hmm.
to reduce by half.
Yes.
Yeah.
So reduce to half of the
To
original
half.
value.
Yeah.
Exactly. You understand? Right?
Mm-hmm.
Nice. Okay. So Yeah. It's the same thing. So the rate at which the number is decreasing, the dn over dt is proportional to is it's not necessary. It's not necessary. Yeah, you can also define it as the time it takes to reduce to 1 over e of its original value. 63% is 1 over e. So just in case. So it is the time taken for the number of excited fluorophore to reduce to 1 over e of its original value. Right? 1 over e is 63%. Okay. So there are a lot of things that affect the value of the lifetime. And that's what we're going to talk about. We're going to talk about the number of things, the things that can affect the value of um, lifetime. Factors that influences the lifetime. Basically, any factor that can make the excited molecule to release energy is going to influence the lifetime. It's going to make the lifetime shorter. You understand? Nice. So any factor that can make the excited molecule release energy will reduce the lifetime. Why? Because the excited molecules will come down to ground state faster. And the time it takes for it to reduce to 63% will reduce. Nice. Okay. So the factors are, what are the factors? Conditional quenching, fluorescence, energy transfer. This is my favorite. Fret, intersystem crossing, rotational motion. Okay, let's start with the easiest because that is how I like life to be easy. Rotational motion. How does rotational motion affect the lifetime? Think about it, think about it, think about
Rotational
it.
motion
Yes,
of the
of the
fluorophore.
fluorophore, yeah. How does it affect the lifetime?
Um, inversely, like the more rotation, the
Think about
okay,
why.
not inversely directly.
Mhm.
Um, it's using more energy
No,
to
it's
rotate.
to rotate is like there's because when you rotate, you can imagine a rotation at different energy levels. So when it's rotating, it's going from higher rotational energy level to lower rotational energy level.
Okay,
So it is losing
energy.
energy. Exactly. Because your rotational motion is just extra way for the molecule to lose
Oh
energy.
yeah, true. Instead of gain.
Exactly. So rotational motion reduces the half-life. You understand, right?
Yeah.
Rotational motion is just an extra way for the molecule to release energy. It's just an extra pathway for excited fluorophores to lose energy. So rotational motion does what? Rotational motion reduces the half-life, the lifetime. Okay, What about collisional quenching? It's the one that sounds scary, but it's also stupid. Collisional quenching.
Collisional quenching.
What is collisional quenching? Collisional quenching. It's exactly what it sounds like. You're
Collisional.
hot and you hit somebody and you quench your hotness. Yeah, so that's just it. So when an excited molecule can bump into another molecule and it transfers some of its extra energy to that molecule.
Okay.
So how is that going to affect the lifetime?
It will reduce lifetime.
Exactly, to reduce the lifetime because it's an extra way to release energy.
Okay.
Nice. So the excited molecule bump into another molecule, bump into another molecule, and what? And
And transfer.
yes, and transfers. Yeah.
But there is fluorescence energy transfer.
That is different. That's fluorescent resonance energy transfer. It's very important. The resonance is very important. And
Can
transfers.
you imagine? Did you write?
Then you write what?
They only wrote fluorescence energy transfer.
Yeah, you see it's fluorescent resonance energy transfer. I can transfer this energy to the molecule. So this reduces the lifetime. Reduces the lifetime. It reduces the lifetime because it makes the number of excited molecules reduce. Okay, what about intersystem crossing? This is a bit hard. Think about it. How does intersystem crossing, sorry, how does intersystem crossing reduce the lifetime?
Um, because it's moving from higher to lower energy level.
What is intersystem crossing?
From S2 to triplets.
You know, from S1 to T1.
S1 to T1, sorry.
Mhm.
Yeah. So the thing changes.
Yeah, there's been changes, but it's not that's not the importance. When you go from S1 to T1, remember to go from T1 to S1 is a forbidden transition, right? Forbidden transition. So what happens to the molecule already here?
It remains there for a while.
Exactly, it remains there. So that means coming back is going to be very slow, right? So they are going to remain excited for a long time.
Okay.
So what happens to the lifetime?
The lifetime increase.
It increases. You understand, right?
Okay, so this is also intersystem crossing.
No, the S1 to T1 is the intersystem crossing.
Okay.
Intersystem crossing. What is this one called?
Phosphorescence.
You understand, right? So intercrossing, intersystem crossing transfers molecules to the T1 state where they remain for a longer period, right? Where they remain excited for a longer period because of the forbidden transition for a longer period because transition to S0 is forbidden. This causes the lifetime to increase. To increase. Okay, so that's intersystem crossing. So the next one, the one that is the longest, fluorescence energy transfer. What is fluorescence energy transfer?
Transfer of energy
Yeah.
from one fluid form to another, I guess.
Yes.
Mhm.
Yes. 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 We'll talk about it later. I mean, it's a bit complicated. There are a lot of slides, right? There's like several slides, right? We will talk about it later. Okay. Homogeneous system, it's not important. It's heterogeneous system, it's not important. Yeah. Fluorescence decay and radioactive decay. So this shows you that fluorescence decay and radioactive decay goes in the same fashion. It goes in logarithmical fashion. This is the time. This is the number of excited molecules. The number decreases in the same logarithmical fashion, right? Yeah. So this is fluorescence decay. Right? You already know the meaning of half-life and lifetime, right?
Yes.
Nice. Okay. So yeah, it uses the same log curve, blah blah blah. Okay, what is a fluorophore? What is a fluorophore? Fluorophore, fluorophore. What is a fluorophore? Fluorophore, fluorophore.
Is particles.
The molecule.
Okay. Fluorescent molecules.
Yeah, it's a molecule that can fluoresce, that can give out fluorescence. It is a molecule that can fluoresce. Okay, now we don't know how to spell fluoresce.
So I have a question.
Yes.
The intersystem crossing, like from T1 to S0,
Mm-hmm.
that is forbidden.
Yes.
But that's not the intersystem crossing.
No, that's not interesting.
Okay. But in those things, the collision quenching,
Mm-hmm.
yeah, so the intersystem crossing.
Mm-hmm. It does
Okay,
yeah.
okay, don't worry.
It does separate from S1 to T1.
T1.
So it makes the molecules in T1 increase, right?
Yeah.
But they're still excited. Exactly. So a fluorophore is a molecule that can fluoresce. So what kind of molecules can be fluorophores?
Um,
So for you to fluoresce, the first thing you need to do is to absorb light, right? It's very important, right?
yes.
So molecules that can absorb light can absorb light. Sorry, absorb light. Usually in the visible spectrum, right? So usually in visible spectrum. So we know from chemistry that molecules with a lot of conjugated pi bonds, a lot of conjugated double bonds, can absorb light in visible spectrum, right? So we need molecules with conjugated double bonds. But yeah, you don't know from chemistry. Why did you nod your head and say you haven't done organic chemistry?
No.
Yeah, so so you don't know that molecules with conjugated double bonds can absorb. Okay, well, molecules with conjugated double bonds can absorb light. An example is these amino acids with conjugated double bonds. They can absorb light. So that's why they can be fluorophores. Nice. Okay. So the next slide is showing you the fluorescence spectra of the different amino acids. So there are only three amino acids that can absorb light, visible light, and it can fluoresce. That's the phenylalanine, thyroxine, and tryptophan. Just to memorize it. These ones, they are the only amino acids with benzene rings. You don't know that already now. You're going to learn it in the sixth week. So
Even 60.
no, not sixth week, sixth week. So just memorize it that these are amino acids with benzene rings. Okay, the next one is just showing you the common fluorophores. They're just, yeah. What does it mean exogenous fluorophores?
Heterogeneous.
Exogenous.
Exogenous. The first light from the outside.
No. No. So they are not from the body.
Okay.
They are fluorophores that are not from the body.
What body, like?
From the human body, yeah.
Wait, so there are
Fluorophores
fluorophores in
yeah.
our body.
Yes. So like the example that they give me here is NADH. And for example, don't forget, we already mentioned some amino acids
Okay.
that can, yeah. So those ones are endogenous fluorophores. So an example of an exogenous fluorophore is ethidium bromide. We already talked about ethidium bromide, right? What
Yes.
ethidium bromide?
That was in
The last topic discussed.
yes.
Said the electrophoresis.
Yes.
Uh-huh.
I forgot.
Electrophoresis, when the ethidium bromide binds to the DNA and they are fluorescent, so they can be able to show the location of the DNA. You remember, right?
Yes.
Bind to DNA.
Ethidium bromide.
Ethidium bromide.
Ethidium bromide. So they are added to the DNA.
Yes, they bind to the DNA
Okay.
so that they can show the location of the bands where the DNA is located during electrophoresis. Okay, common fluorophore is key. Some applications of fluorophores. Okay, let's talk about some applications of fluorophores. What are some applications of fluorophores? The most important one is the immunofluorescence ion sensitive dyes, membrane potent. Okay, all of them are important. So just talk about immunofluorescence. What is immunofluorescence?
Immunofluorescence.
Mm-hmm.
Immune system first.
Oh my god.
Immune
Yes.
antibody.
Yes. So when the fluorophore dye is attached to an antibody,
Okay.
it can give you immunofluorescence, right?
Mm-hmm.
So if fluorophore is attached to an antibody. Okay, ion sensitive dyes. These are just dyes that can change distribution or they can change their structure or their, they can go from acid to base based on the kind of ions that are present. Mirror like indicators, some indicators that are fluorescent. You understand, right?
Mm-hmm.
Nice, that's it. Membrane potential fluorophores. These are fluorophores that can move from one membrane compartment to another membrane compartment when there's a change in membrane potential. You understand?
Mm-hmm.
Nice. That's membrane potential fluorophore application. Okay, DNA dyes, these are just fluorophores that can bind to the DNA, like ethidium bromide. Determination of protein fluorescence, these are just fluorophores that can bind to proteins. Okay, measuring fluorescence. Oh my god, the things in this lecture slides.
It's
Measuring,
long.
I know it's long. It's long. What are we in? We
It's
just 29 or, or 30. What number are we in?
one 29.
29 out of 58. So you're just halfway done.
Okay, what's that picture?
Yeah, but still, most are supplementary material, but still.
Right.
Oh no, so you messed up.
How we should go to friends?
No, we have to get through it step
Okay.
by step.
Wow.
Okay, this is discouraging. Let's continue. I'm just tired.
Photo bleaching.
Okay, so measuring fluorescence.
Measuring fluorescence. Okay.
So the first one is the spectrophlorometer, obviously. You know the fluorometer, right?
The
Fluorometer.
mhm.
Fluorometer measures fluorescence, right?
Mhm.
Yeah. Okay, so let's just measuring fluorescence. So a fluorometer can measure what? Fluorometer measures,
Fluorescence.
yes, the, yeah, usually the emission spectra, mostly, right? Of fluorophores. What about the fluorescent microscope? What does it measure?
Fluorescence
Yeah.
microscope.
Mhm.
Did it measure?
What does it do? What does it?
Oh, it fluoresces some molecules.
Yes, so it detects the locations of the fluorophores in a cell or in
Okay.
an image. So it
Okay.
can be able to show you, it can be able to provide an image of a sample based on the location of the fluorophores. You
Okay.
understand that? So it gives an image of a sample based on the distribution of the fluorophores in the sample. Okay, you understand, right?
Yes.
Yes. Okay, so measuring fluorophore. Okay, let's talk about filters. Filters are very important for fluorescence. We have already mentioned one type of filter so far. That's the monochromator.
Online measuring fluorescence, there are no calculations.
No, I mean
Can
they can
you
actually
see?
calculate the photon yield.
Okay.
Oh, that's basically it. Okay, so let's talk about the filters. What are filters?
Filters, they used to like take away
Hmm.
like unnecessary stuff.
Yes, certain wavelengths.
Okay.
What's this? So filters remove. Oh. certain wavelengths. Okay, so we can have filter before, if you have this, if this is a sample, yeah, this is the light source. You have the monochromator. This is basically a filter because here you have white light, maybe if you have white light, and allows just one type of wavelength to pass through. Usually it allows only the wavelength that is the excitable light. You understand? It's not going to allow light that has low energy that cannot excite the sample to pass through. It's going to allow high wavelengths, high energy light, right, to pass through. And then it reaches the sample, and then the sample gives out, and then you pass through this another filter, and then you get to your detector. This filter here is going to remove, well, it's not going to be in this direction. Maybe we don't put it in this direction if we are measuring fluorescence. What direction do we put it?
90 degrees.
Exactly, 90 degrees. Why do we put it 90 degrees?
Because of emission.
No,
The
because of transmitted light.
transmitted
We don't
light.
want to get the transmitted light, right? We don't want to measure transmitted light,
Okay.
right?
But we're detecting
What are we detecting?
emitted light.
Emitted light. Emitted light usually have a longer wavelength than transmitted light, right?
Okay.
You understand, right? Okay.
So there'll be two detectors.
No, this is not. This is not. So it's here. Come here. It passes through here, right?
Mm-hmm.
And then reaches the detector, right? Some of this light is going to scatter in the sample, and then it's going to also go in this direction. Do you understand?
Mm-hmm.
Nice. So if it goes in this direction here, we want this filter to remove the light that scatters in the sample, right?
Mm-hmm.
So now this filter is going to remove that. You understand?
Yes.
Nice. So first thing that we do to prevent transmitted light is to put it at 90 degrees. Another thing is to put another filter here. So it filters light, let's say emitted ex excitation light. So excitation light from the light source that scatters in the sample and comes towards the detector. You understand that?
Yes.
Nice. You know what scattering is?
Yes.
What is scattering?
Scattering, like in light, in terms of like going in like different directions.
Exactly. So it passes through the sample and goes in different directions, right? So it's not like smooth transmission or smooth reflection. It's a bit in between.
Okay.
Nice. Exactly. It's twisted. Okay. So this is long. I don't think we're able to finish it today, right?
Nope.
We can continue tomorrow or next time.
Tomorrow morning.
Okay. So we just start class, yeah.